Hi, welcome to Sam's Maths channel. Today I'm going to be introducing the concept of a group and sort of its basic mathematical structure. So groups arise quite naturally in mathematics and physics as a way of manipulating an object without changing certain properties of that object. So we're sort of exploiting the symmetries in a basic mathematical way. So if we take, for example, this regular triangle here, and if we sort of label its vertices A, B, C, then we can look at the ways in which we can change that triangle, which sort of leave it as the same triangle so it looks the same, we don't tear it apart or anything. So we can leave it the same, like this. We could rotate it clockwise by 2 pi by 3 degrees, which would leave us with a triangle A, B, C. We could rotate it anti-clockwise, A, B, C, like so. And then we could reflect it about any of these sort of three axes here, which would give the triangles A, B, C, A, B, C, and A, B, C. Okay, so what's important here is that we can sort of take any of these and combine it with another one, and we'll end up with a third transformation of that, and that's sort of what we want with a group. Okay, so mathematically, a group is sort of we write it like this, as an ordered pair of a set G and a binary operation dot, which sort of takes two elements from G like this, and returns another element of G. It sort of always has to return another element of G. And it has to follow the three axioms that, such that we need associativity. So for all F, G, H, we'll call them, in G, we have the F dot G dot H is F dot G dot H with the brackets around the other way. So what this means is that sort of the order of operation doesn't matter. It's like when we add numbers, we don't care which we add first. And so that basically means we don't need brackets, which is quite useful. We then have this thing called a left neutral element. So there is some element E in the group, which means that for every other element G in that group, we have the sort of E dot G is equal to G. So E is this thing that we can operate on another element and nothing will change about it. Okay. And then finally we need a left inverse. Okay. So for every G in G, then there must exist a sort of G twiddle of G such that G twiddle dot G, so doing G and then G twiddle, is the same as doing nothing. So G twiddle sort of undoes G. We want to be able to undo all of our operations in some way that's important to us. Okay. And so we can check that our triangle is indeed a group. So if we take any of these two, I'll leave it up to you to check that a combination of any two will then be a third member of that group always. It's not too hard to see. It's also obvious that this is associative because sort of F, G, H, so sometimes we omit the dot if the dot is obvious, is do H then G then F, because we sort of take our set of operations and we say that F, G is do G then F, because that's how we work with functions. So we get this, which is just the same as doing H and then G and then F like this. So it's associative. We then have this identity element here. If we do nothing, that's not going to change anything. And then we have an inverse. So these two sort of invert each other. If we rotate it clockwise and then anti-clockwise, that undoes it, and vice versa. And then leaving it alone, and the three reflections are sort of their own self-inverses. So quite clearly we have a group here. So that's good. We've sort of designed a structure and it does what it should have done. Okay, so there are some other points that we can make about these sort of group axioms that extend them to be more useful. Lots of authors will just include these in the axioms, but sometimes it's nice to sort of start as basic as it goes. So we have that a left inverse is a right inverse. So left inv is right inv. Okay, so if we let G in G, okay, then there is a G twiddle in G such that G twiddle dot G is E, but then because G twiddle is in G, then there must be a G dash in G such that G dash inverts G twiddle, okay, because obviously that's just one of our axioms, that's something that we've said is true, okay. So this means that G dot G twiddle, so this is, if we're using it as a right inverse, is equal to E dot, because we can apply our left inverse. And so this is equal to, using this definition of E here, G dash dot G twiddle dot G twiddle, because we can drop the brackets by associativity. And this is obviously E again, because by definition, which we can then remove because by definition, so we get G dash dot G twiddle, which is E. Okay, so our left inverse is also our right inverse. And so some authors take that for granted. And then a left neutral is also a right neutral, using sort of a similar argument. Okay, so if we let G in G again, and then we have that G twiddle is also in G such that G twiddle dot G is E, and also that is going to be G dot G twiddle by the sort of the previous statement. Then we have that G dot E is G dot G twiddle dot G is E dot G by sort of compacting these two into an E, which is just G again. Okay. And then we have sort of a couple more. So the neutral is unique, so we can only have one identity element. So suppose that we'll call them U, V, have for all G and G. U dot G is G and V dot G is G. Then, and obviously these two both belong to G. Then obviously U dot V is equal to U is equal to V because they're both left neutrals, so we can just apply U. But then we have that any left neutral is a right neutral, so U dot V is equal to U, so V is U. It's quite an obvious proof, but it's good to write it down. And then the inverse is also unique. Okay, so let G and G again, and let G twiddle and G prime have that G twiddle dot G equal G prime dot G equal E. Okay, so they're both left inverses. Then that means that G twiddle is just E dot G twiddle because we can apply the left neutral, which is going to be G dash dot G twiddle by using this one. But then any left neutral is a right neutral, so that's going to be G dash dot E, and that is G dash. Okay, so the inverse is unique, and we write this then as G minus 1 dot G is equal to E, because we sort of think of groups as multiplication, so it makes sense to use this notation. And then because we have that G minus 1 dot G is G dot G minus 1, which is E, then it means that the inverse of G is just G, which is sort of a nice, easy property. Okay. So using this, we can sort of define a power of an element. So for n in the sort of positive integers, so we'll call these z plus. So 1, 2, 3, 4, 5, and so on. And G in G, then G to the n is defined as G dot G dot 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 G, so that we have n copies of G, sort of just like when we have powers of an integer. And G to the negative n is then going to be defined as G to the minus 1 to the n, and that happens to also be G to the n to the minus 1, and then we let G to the 0 equal E, which gives us sort of a nice useful, so for all G in G and for all m n integers, so positive or negative, we have that G to the m dot G to the n is equal to G to the m plus n. Okay. So one thing that we haven't sort of talked about that is usually a property that we quite like but don't always have is if for all G and F in G, we have that G dot F is equal to F dot G, then this is sort of an extra property. So we say that G is abelian. Okay, and it's important to remember that not every group is abelian. Lots of nice groups are, but lots of other groups are not. So when we talk about later groups of matrices and so on, they're often non-abelian. Okay, so I think that's about enough for today. We'll be coming back next time to talk about sort of subgroups, product of groups, and maps between groups or homomorphisms. Okay, thanks for watching.